This is Covalent Molecules, which is Chapter 8 in your book. First, I want to do a quick recap of ionic bonding, which is in Chapter 7 in your book. So, in ionic bonding, you have two atoms, a metal and a nonmetal, so for example, sodium and chlorine. And what happens is they each want a full valence shell. And so chlorine is so much more electronegative than sodium that it actually takes sodium's valence electron, and then both atoms end up with a charge. Chlorine with a negative charge because it took an electron, which is negative. Sodium with a positive charge because it lost an electron, and so it has an extra proton compared to electrons. Now, I think it's really obvious from this diagram that chlorine then has a full valence shell with its 8 electrons. I think it's less obvious that sodium does, but that's why I wanted to make sure to write in sodium's electron configuration: 1s2, 2s2, 2p6, 3s1. The electron that was just given to chlorine is this 3s1 electron. And so with that out of the picture, now you'll notice sodium's valence shell is the second principal energy level, and that's full. That is 8. So then sodium and chlorine both have charges, opposite charges, and so they attract to each other, and you get sodium chloride, and you get this nice crystal lattice, ionic crystal lattice, where you have, again, we can talk about, if we look at kind of the least common denominator, or the smallest ratio, that would be 1 formula unit of sodium chloride, which is 1 Na and 1 Cl, which is why we call it NaCl. And then we talked about if you were to put the solid NaCl in water, the ions would dissociate, and then you could conduct a charge between the positives and the negatives. Now let's compare that to covalent bonding, which is Chapter 8. So in covalent bonds, you end up, as we talked about, when they dissolve in water, the atoms don't dissociate at all. You may end up with one molecule of a substance, but it's still one molecule of a neutral substance. We also talked about the fact that covalent bonds generally have lower melting and boiling points than ionic compounds. And we also talked about the fact that covalent bonding is between nonmetals, whereas ionic bonding is between metals and nonmetals. So the big difference, though, in the bonding is that covalent bonding results from a sharing of electrons in nonmetals to gain an octet, which is a noble gas structure, 8 valence electrons, with the exception of hydrogen, which only needs 2 valence electrons because its noble gas structure would be helium, so 1s2 would be a full shell. So let's take hydrogen and chlorine. Instead of one of these atoms taking an electron from another, if this were sodium and chlorine, the chlorine would take the electron from the hydrogen. Instead, the two atoms share the electrons. And part of the reason for that, as we're going to see later, is the difference in electronegativity between chlorine and hydrogen is much smaller than the difference in electronegativity between sodium and chlorine. And so because the difference in electronegativity isn't as large, chlorine can't just pull that electron away. And now both elements have a full octet. So chlorine has its 1, 2, 3, 4, 5, 6, 7, 8. Hydrogen only needs 2, so it has 1, 2. What you need to understand is these 2 electrons here are shared between the 2 elements. They both get to count them. And we write it like this. So what we've done is we take the 2 electrons that are shared, these 2 electrons, and we draw a single line to show a single bond between the 2. So each bond is 2 electrons. And that's what covalent bonding is. Now, occasionally, you need more than one bond, more than 2 shared electrons, for each element to get its octet. So let's take the example of carbon dioxide here. In carbon dioxide, you have 1 carbon and 2 oxygen. Now, generally speaking, although certainly not always, the first element you see is going to be the central element. So carbon, I put it in the center because it's the central element here, and we have 2 oxygens. If we continue with what we had earlier, what we would see is a sharing of these 2 electrons and these 2 electrons. And so what you would end up with would be this structure. The problem with this is that none of the elements actually have a full octet. So if you look at oxygen, it has 1, 2, 3, 4, 5, and then remember, the bond is 2 electrons, 6, 7. The same with this oxygen, because it's basically a mirror image. So they only have 7. Carbon's an even worse situation. It has 1, 2, 3, 4, 5, 6. So neither has an octet. So what needs to happen in this situation is more sharing. If people don't have what they need to do a little more sharing. So I didn't draw these electrons very well, but this electron and this electron can be shared, and this electron and this electron can be shared. And then the way you would write that is like this. And now each atom has a full octet. So oxygen has its 4 unbonded electrons plus 1, 2, 3, 4. That's over here 1, 2, 3, 4. Same with this oxygen, so 4 plus 4 is 8. And then the carbon has 1, 2, 3, 4, 5, 6, 7, 8. So each atom has a full octet in this case. And that's called a double bond, where 4 electrons are shared between 2 atoms. Sometimes you need a triple bond. So let's take the case of N2. This is nitrogen gas. It's a diatomic gas. Di meaning 2, atomic meaning atoms. So it's a gas with 2 atoms. Most of the gases that we think of as far as when we think of element gases are diatomic. So nitrogen that's in air is actually N2. Oxygen is O2. Chlorine gas is Cl2. So those are all diatomic gases. So in the case of nitrogen, nitrogen has 5 valence electrons. We can see if we only share, say, these 2, then each nitrogen is going to have 6 electrons. So we can also share these 2. Now each atom is going to have 7 electrons. So we can share these 2. Now each atom will have 8. It will have the 6, 1, 2, 3, 4, 5, 6 that are shared, plus each atom has 2 unbonded electrons. 6 plus 2 is 8. And so we would draw that like this. Nitrogen with what's called a triple bond, 6 shared electrons between 2 atoms, and then the 2 unbonded electrons. What's really important, and I've seen students mess this up before, a triple bond is not just 3 bonds. It's 3 bonds between the same 2 atoms. A double bond is not just 2 bonds. It's 2 bonds between the same 2 atoms. So in the case of carbon dioxide, we actually have 2 double bonds. This is 1 double bond. This is the second double bond. So just kind of keep that in mind, that it's not just 2 bonds, it's 2 bonds between the same 2 atoms. So let's look at polarity, which is an unequal balance of charge within a molecule. And ignore these numbers at the bottom of the screen here. That's my screw up with the animation. We'll need them in a few minutes, but just kind of ignore them for now. So a polar molecule is when one atom in a molecule attracts the electrons more strongly than the other atom, which results in a slight positive charge on one atom and a slight negative charge on the other. The part of the molecule that's attracting the electrons more strongly would have a slightly negative charge because it's got it gets an undue share of the electrons, whereas the other part would have a slightly positive charge. So most of you have taken biology, and I know you talked about how water is a polar molecule. And that means that water is covalently bonded, but that the oxygen in the water attracts the electrons slightly more strongly. It has a higher electronegativity than the hydrogen. And so the oxygen side is slightly negative, whereas the hydrogen side is slightly positive. Not strong enough to be an ionic compound where the oxygen actually takes those electrons. But again, think back to sharing. It would be like if you're sharing a sandwich, say, but somebody eats 3/4 of the sandwich and the other person only gets 1/4. It's still shared, but it's not an equal sharing. And polarity, as we were just talking about, results from a difference in electronegativity. So let me show you how this works. This is where these mystery numbers on the bottom come in. What I might do right now is pause the video, and if you don't have your book, get it and open up to the periodic table with the electronegativities on it. So hydrogen, here's hydrochloric acid or hydrogen chloride, as we saw earlier. Hydrogen has an electronegativity, as you can see, of 2.1, whereas chlorine has an electronegativity of 2.5. Chlorine is more electronegative, meaning it's going to, these two electrons that it's sharing, it's going to pull those electrons just a little more towards the chlorine than the hydrogen. So it's going to get maybe more of the sandwich than the hydrogen is if we're talking about sharing a sandwich. Something like nitrogen gas that we just saw isn't going to be polar at all because the nitrogens both have the same electronegativity, so they're going to equally share the electrons. So what we draw is these funny kind of like S's that then loop around, or partial 8s. And what that actually is, that's the lowercase delta. You remember delta, the big triangle that means change? So the lowercase delta is a partial charge. And so chlorine has a slight negative charge. Hydrogen has a slight positive charge. It's not a full charge, otherwise it would be ionic, but it is a slight charge, and so that's how we designate that. As we talked about, you can look at electronegativity and then determine how polar something's going to be. And really, there's a continuum, but you can divide molecules up into ionic, nonpolar covalent, and then in the middle, polar covalent. There's actually also metallic bonding, but we're not going to worry about that. Depending on how you want to break this up, you could even talk about slightly polar, very polar. We're just going to talk about polar. And so if the difference in electronegativity is anywhere from 0 to 0.4, we're going to say that is a nonpolar covalent molecule. So like Cl2. And you can see if we show kind of a picture of the orbitals here that that electron probability or electron density is shared equally between the two chlorines. Between 0.4 and 2.0, we have polar covalent. So like hydrochloric acid. And in fact, if you remember from the last slide, hydrochloric acid's difference is 0.4. So it's really right on the border. It is slightly polar. It is polar, but only slightly so. And so you can see in this picture, the electrons are pulled a little more towards the chlorine than towards the hydrogen. You could even look up pictures where you can see differences in, say, hydrochloric acid, and then how polar hydrofluoric acid or hydrobromic acid is, looking at all of those halogens as you go down the list. And you know the trend for electronegativity. You can probably predict which is going to be the most polar. Hydrofluoric, hydrobromic, hydrochloric. It might be interesting to make that prediction. And so then anything that's got a greater difference in electronegativity than 2 is ionic. So for example, NaCl. And in this case, it's not just that the Cl gets slightly more of the electron charge. It's that it actually takes an electron from the sodium and becomes an ion. And so here's an example. I like this example because it's got chlorine in each one, and depending on what the chlorine is bonded with determines how polar and what type of bond it is. So here's an example. What type of bond is hydrofluoric acid, HF? So go ahead, look at your electronegativity chart and determine that. So you should have seen that hydrogen has an electronegativity of 2.1. Fluorine has an electronegativity of 4. If you didn't see that, please look at your chart. And so 4 minus 2.1 is 1.9, making hydrofluoric acid polar covalent. And in fact, kind of the opposite of hydrochloric acid, hydrofluoric acid is very polar. It's so polar, it's almost ionic. Remember that fluorine has the highest electronegativity at 4.0. And so hydrofluoric acid is kind of on the opposite end of the polar covalent spectrum from hydrochloric acid. So earlier I was drawing Lewis structures. Those were all those lines and dots. So there's some rules for drawing Lewis structures. First, you're going to count the total number of valence electrons for all the atoms in the molecule. Then you're going to write the symbols for all the atoms to show which atoms are attached to which, and connect them with single bonds. Always start with single bonds. And again, usually the first atom is the central one, although not always. You're going to complete the octets around all the atoms bonded to the central atom with the valence electrons that you counted in the first bullet. Then you're going to place any leftover electrons on the central atom. If there are not enough electrons to give the central atom an octet, try using multiple bonds. So there's two things we're going to get to later. Later we're going to get to the shape of the molecule, so like why water is kind of a V shape, why carbon dioxide is like a line. We're not going to worry about that right now. There are also some exceptions to the octet rule, such as when there is an uneven number of total valence electrons. And we're going to talk about that in class. I'm going to show you an example of that. But that's also in your book, so you can look at that as well. So, to practice, let's draw ammonia, NH3, or nitrogen trihydride. So, what I would recommend doing is trying to draw it on your own. Pause the video right now. But if you are completely lost, I'll walk you through this one, and then you can try the next one. I've got two examples. So, as we said, the first atom is usually the central one. It's not always the case, but what is always the case is hydrogen, because it only has one valence electron, only ever bonds once. So it can never be a central atom. It's always got to be on the outside because it can only have one bond. It only has one valence electron. So we're going to draw this. Now let's kind of break it down. The total valence electrons from nitrogen is 5. Hydrogen is 3 because we have 3 hydrogens each with 1. 5 plus 3 is 8. The total number of bonds we have right now is 3. Each bond, remember, is 2 electrons, and so that's 6 electrons. So we still have 2 remaining valence electrons. So first we want to place them on the electrons bonded to nitrogen, except that those are all hydrogens. They have their full octets because they only need 2. So we're going to place them on the central atom, nitrogen. And that's exactly what nitrogen needs because it had 6 electrons from the shared ones, and so it needs 2 more to complete its octet. Those unbonded electrons are really, really important in determining the shape of ammonia, and so it's important to understand where to put them. And then later this week or early next week, we're going to talk about shape and why those electrons are so important. So now I really do want you to pause the video and look at dicarbon dihydride, or acetylene is another way of saying this, or even ethyne is another way of saying that. And we'll talk about what those mean later. And try to draw the Lewis structure for this. Okay, so this is what you should have gotten. You should have started with carbon as the central atom, because remember, hydrogen can't be a central atom. And so we've got the 2 carbons in the middle with the 2 hydrogens. Now, let's break it down again. So the total valence electrons from carbon is 4 per carbon times 2 is 8. From hydrogen, it's 1 times 2 hydrogens is 2. 8 plus 2 is 10. Here we've got 3 bonds, which is 6 electrons. which means we have 4 remaining valence electrons. We're not going to put them on the hydrogens because, again, if hydrogen's bonded, it's got its 2, it's good. So we're going to put them on the carbons. However, each carbon does not have a full octet. Each carbon only has 6 valence electrons. The 4 from the 2 bonds that it each has, plus the 2 unbonded ones. And so this is where we need to use double and triple bonds. In fact, this is a triple bond. So if these electrons then are shared between the 2 carbons, then each carbon does have its 8. And so we can do this. So now each carbon has 8, the 6 here plus the 1 here, 6 here plus the 1 here. The hydrogen has its 2, and so there are no remaining valence electrons because now we have a total of 5 bonds, which is 10 electrons, which is exactly how many we had. Please make sure to look this over in your book. Either come to class with questions or add them to the comments section of the YouTube video. And tomorrow we're going to practice drawing Lewis structures. Have a good night.